Okay, so let's start our today's colloquium. We are very happy to have Professor Urbasi Sinha from Raman Research Institute, and she will talk about photonic quantum technologies. And welcome, Urbasi, and I hand it over to you.
Thanks a lot, Arpun. So it's a special pleasure actually to be giving this colloquium at IIT Gandhinagar. Arpun is of course also a little bit like family, so he's one of the first students of my husband actually. So then it's actually a dual this thing. So I hope I do justice to this invitation. As Arpun mentioned, I'm going to talk on photonic quantum technologies, and I head what is called the Quantum Information and Computing Lab at RRI, Bangalore. Okay, so let's see. Yeah. So of course, on a good day, in a good year, it would be nice to have lab visits. And so this is what you would see. Usually in the lab, lots of different optical tables with lots of different alignments. And some of them are cleaner than usual because they are, picture perfect. But then having said that, this is how our lab would usually look. And we have what is called a class 10,000 clean room. Which means that we have less than 10,000 dust particles per cubic foot. And so the whole point is to try and avoid those interference patterns from dust particles because we are measuring, various precision experiments, right? So we don't want unnecessary interference to come in. And so that is the general structure of the lab. What we do is, apply, different applications of photons. So single and entangled photons to different quantum information applications. So whether it's quantum computing, quantum communications, as well as fundamental tests of quantum physics and quantum optics themselves. And so then there is a plethora of activities that is going on at our lab. And in fact, if for students who may have joined who are interested in figuring out how to actually make these photons, because it's easier said than done. You cannot just take a strong light and just put a lot of filters and get the statistics that a true single photon source would give you. And so in order to do that, to harness entanglement, you have to work on the technology. And so this is a review article which may be helpful for that purpose to know more about photon sources. So this is an example of, an entangled photon source in our lab. And as you can see, can you see my cursor? Arpun, can you see my mouse, this thing moving?
Yes.
Great, okay. So then here you can see that, these are the two rings which are the result of what is called parametric down conversion. And so if one of the photons is here, its partner photon is also, it's in the other ring. So this of course comes as a result of several phase matching equations that you need to solve and so on. But this is how it looks on a very intensified camera. And so then this is an actual picture from the lab. And so here at this intersection point, you do not really know which photon you're dealing with, because of course, it could belong to either of the cones. And so this point actually is the point where you see the entangled state. And so if you are interested in an entanglement-based application, then one has to work with photons from this point, otherwise from anywhere else in the cone. And so they are correlated photons, which may or may not be entangled. And so this is the, and there are different types of, entanglements you can create and different types of correlations you can create, and that forms the basis for several of our applications. As mentioned in the abstract also, I will go through a little bit of detail for some of our work, but given the, the colloquial structure of this talk, I will restrict it to, things with no equations, so to speak. But then just a brief overview of the next couple of minutes of the various things going on before zooming in to some of them, because I would not be able to talk about all of them. And so, as I mentioned, we work on fundamental tests of quantum mechanics itself. And here on the left, you see our body of work on superposition principle, on the Born rule for probabilities, which I will discuss in greater detail. And on the right here, you see our experiment on the Hong-Ou-Mandel effect in quantum optics. Again, I will discuss that. Similarly, for the experiment below on our quantum state estimation problem. This is something which I won't be able to discuss in detail, and this is our studies on entanglement measures and studies of entanglement dynamics. So as you already know, entanglement is a very important resource for various quantum information tasks. And so one of our explorations, and we have done several things in that domain, is to actually study different properties of entanglement and understand them better, whether it's static or dynamic properties. Here you see our experiment in progress for the dynamic properties, which means that when you have an entangled state, it interacts with the environment. And then it also kind of decays with time. The entanglement can decay with time. And there is a process, there is a sudden process which can happen, which is called the sudden death of entanglement, which means that at a finite time, the entanglement can go to zero. And this is something you do not really want if you want to hold on to that entanglement for the applications. And so here we have an experiment where we are manipulating the sudden death, making it happen later or never at all. And so, in fact, in these papers, we have showed how to do that. And at the moment, our experiment is almost done regarding the first demonstration of sudden death manipulation in the lab. And this will be very useful because it can be taken over by other systems like solid state ones as well, where they can hold on to entanglement for longer for various applications, including, let's say, error correction and so on. And so this would be the proof of principle test bed using photons that we are almost completing. Here we have a body of work on what is called generalized measurements or weak measurements as a tool. Again, this can form a talk by itself. But then having said that, what we are trying to do in all these explorations is try to find out more about what happens between preparation and measurement. So we all know that when we prepare a quantum state, after that, it goes through some evolution, right? And so that is fine. And then, of course, we have a measurement. But if we do something during that evolution, if we do it in the strong von Neumann measurement sense, then, of course, we collapse the wave function, so to speak. But then weak measurement is a tool by which, doing an ensemble of measurements, we can actually gain information about what is happening in between preparation and measurement without disturbing the system. And so we've done a lot of work on this, some, in fact, in collaboration with Arun, who's in the audience today, I find. And so a lot of interesting stuff can be done, which would be quite unthinkable in the strong conventional sense. And so this is one area. Now going on to, now I would like to go on to some of the details regarding some of the work, and then, you can look up more if you're interested on our website and so on. So the first thing I wanted to discuss a little bit is actually our most recent work, which is on, again, in collaboration with Arun, which is on a new technique for quantum state estimation, okay? So now, why is that important? So, well, of course, we are talking about quantum, measurement. We're talking about quantum information applications. But what is the first thing that happens? That is, of course, the quantum state, right? And then that is where you apply your operators. You do what you want to do. But then how do you estimate the quantum state? Because, of course, that is the whole point. So if you actually have a direct measurement to do that, then you will, of course, not be able to use that any further because it has collapsed and so on. So there are techniques to do this, and the conventional one is called quantum state tomography, which is very similar to, in an example form, like the CT scan, So we know of the CT scan of, let's say, the brain. And so what do? We want to image the brain. So we are actually projecting the brain, different slices of the brain. We have images of different slices, and we reconstruct the image from all these slices, right? So that is what we do with the quantum state. So we have different projective measurements, and we reconstruct the density matrix from these measurements. And this is called quantum state tomography, okay? What we have established, we have come up with the methodology as well as in experiment. We have shown that we can alternate this by using what is called quantum state interferography. And what is this interferography? This is not using tomography techniques. What we have done here is we have this, let's say, the quantum state. It is incident on an interferometer, and that could be of different types, and those details we won't get into here. But the idea is that the interference pattern that you measure, or the interferogram, that actually has information which can be used to reconstruct the state without changing any of the settings in between. So you have a state, you have the interferometer, and then you have the interferogram. And then from the interferogram, you can reconstruct the state without changing any settings during the measurement. So by a single shot measurement, which means no change of settings, we can estimate the quantum state. And this is very nice because it gives us a tremendous scaling advantage over quantum state tomography, where, of course, we have to have different settings for these different projections. And, so do have a look at the paper if you're interested, because this, there's a lot of detail which I'm skipping here. But the idea is that this quantum state interferography can be used to determine an unknown qubit state using a single shot measurement. And if a bipartite state of qubits is known to be pure, if a pure bipartite in a qubit state, then QSI can actually quantify the entanglement in that also with a single setup. And so if you are in the business of measuring entanglement, you would know that a bipartite qubit would be a density matrix with, let's say, 16 elements. So then if you wanted to reconstruct that, then you would need, let's say, at least 15. But if you made the pure state assumption, then you get rid of the top half, then it'll be a finite number, let's say 7 of measurements that you would still need in order to reconstruct this. But then in QSI, by this single shot scheme, we can actually do that. And so with 2 interferometers, now if you want to actually now scale the dimension higher, so of course qubits is fine, but what happens to a qubit, which is d greater than 2? So if you now talk about a 3-dimensional system or a 4-dimensional system, then of course the tomography requirements go n square, so d square. So it is very large, the number of measurements you need in order to reconstruct. And however, for our QSI, with 2 interferometers, any pure qubit state can also be determined. So this gives us a fantastic scaling advantage over conventional quantum state tomography. And also it actually relies on one of the most fundamental, what should I say, measurements that we can do as a quantum experimentalist, which is interference. So interference is, of course, what captures the heart of quantum mechanics, as Feynman said. So this is a resource, yet again, but in a completely new avatar. And so that is what is quantum state interferography. But bear in mind that we are not really, bypassing quantum mechanics in any way. This was asked in a talk I gave where this was discussed in more detail. That's not the point. The point is we actually gain more information from that single interferogram. And that is why we are able to do this. Okay. And so this is one of our recent experimental results on quantum state estimation. Going on to our work in quantum computing, well, of course, quantum computing is something I'm sure is something that you all very much are aware of, that there is a lot of activity going on currently, both in India and of course, especially worldwide, where there are lots of claims from various companies as well as research groups on, quantum supremacy and so on and so forth. So the whole world is buzzing with this quantum computing named, application. And so what we are doing in our lab is approaching this in a different way. So instead of working with qubits, which of course you're familiar with, which is 2-dimensional systems, we are actually working with higher dimensional systems towards quantum computing as well as some aspects of quantum key distribution. And so what does that mean? So again, for the students specifically, an invited article that I wrote for Scientific American would be very useful, where I have actually discussed this particular work that we are doing on higher dimensions and how we are approaching quantum computing problems through this technique. And so do have a look. So now going on to higher dimensions. So what does that mean? So this is a slide which helps in understanding that. So an example that I like to give in a general talk is, of let's say a football match or something. So if you have a football match and if you want to declare the results from this match through quantum techniques for some reason. Okay? And it was in fact done. In South Africa, this World Cup results were actually declared using quantum communication. I think the one before last World Cup. But anyway, so that of course is for the security purpose. But in general, there could be different types of results for this match. It could be, let's say, team A wins, team A loses, there is a draw, and maybe there is a rain abandoned match. Just I'm coming up with examples. The first 2 I've heard of, third also, but the fourth one is my imagination. Perhaps I'm not into football much, but these are 4 possibilities I can think of. And so if I want to declare these results, if I use a single qubit, the 2 states of the qubit can only encode 2 possible results, let's say win and loss. Similarly, the second qubit also, we can do the rain abandoned and the draw, but 2 qubits would be required to declare this result. So now if I had what is called a Q quad, which is a 4-dimensional system, then I can actually declare the results using one Q quad itself. So what this means is, now if you think about it from a more actual implication perspective, we can have access to a similar dimension of state space using a smaller number of higher dimensional systems than what we would, similar to what we would do with larger number of qubits. And that is actually very nice because of course, this 50 qubits and the fact that 50 is important, all this we have heard, but it has taken us several decades to reach this 50. which means that, when you go beyond a certain number and you want to put these qubits in coherent superposition, it becomes a problem, because the qubits don't want to be in a coherent superposition beyond a certain number. And so that brings, decoherence, so on and so forth. So if you can deal with a smaller number of systems, that has obvious advantage over a larger number of smaller dimensions. So this, but then of course, there is a lot that is left, there is a lot that is to be done in the qubit domain. The right protocols, the right set of gates, the single qubit, multi-qubit gates. So there is a lot of interesting research to be done, with the promise that it gives you a system which definitely has certain advantages over the more popular counterpart. And so that is very interesting for us as a research group, because of course that is what we like to do, come up with interesting ideas which we can implement both theoretically and experimentally. Right? And so this is what a qtrit is. As I was saying, it's a three-dimensional system. So instead of alpha 0 plus beta 1, which is your qubit, we have alpha 0 plus beta 1 plus gamma 2, say, where 0, 1, and 2 are the three basis states. And so now think about a single photon, which is incident on, a plane which has three apertures, okay? So the photon could go through either A or B or C. And so because we don't know which one it is going through, it forms the superposition of alpha A plus beta B plus gamma C, which is a three-dimensional system. So this is one way in which you can encode higher, higher dimensions on a single photon. Because of course, if you think about polarization, you can only have two dimensions, right? H, V, or plus, minus, and so on. So if you want to go to higher dimensions using a single photon, one of the methods of doing that would be this sort of a spatial encoding, okay? And so regarding the qtrit, as I mentioned, of course, the quantum computing advantage is what I was talking about, but qtrits are also known to be more resistant to noise than qubits. In quantum cryptography, the use of qtrits was proven to be more secure against digital attacks. And for people among us who like to understand better the fundamental aspects, qtrits are known to violate local realism stronger than qubits as well. And so these are all actually, there's a lot of research in the, which has happened in the theoretical domain using higher dimensions, but not as much parallelly in the experimental domain, in the actual practical domain. And so that is where we want to come in with our own system, which is our indigenous system, where instead of actually having a photon incident on three slits, we have modulated the pump, beam, and down conversion and come up with a system where the crystal, the nonlinear crystal itself, generates pairs of qtrits as we speak. And so this is what we call the pump beam modulation technique for generation of higher dimensional systems, which actually we have found for the first time in our lab, this pump beam modulation technique. And so this is something which we are using, which has a definite advantage over, yes.
Hi, may I ask you? Hi, Prasanna.
Yes, please. Yeah, hi, Prasanna.
So I was wondering, in the three-slit example, if it's just spatial modes, there is, in principle, they are not necessarily completely orthogonal, right?
No.
So in this case, you have in your experiment, they are actually orthogonal, is it?
So what we are doing here is, so now, when you talk about the lack of complete orthogonality, maybe you are referring to these interaction terms which can happen between the slits themselves, which of course we have also investigated, which I will come to next actually. But then having said that, before I come to that, in case of slits, we are not doing that. So as I said, that what we are doing is, instead of the photon being incident on three slits and generating your qtrit, we have the pump beam in the down conversion itself taking on the form of the three slits. So what you see here, this is the pump, okay? This picture is of the pump. And so this is incident on the crystal. And so what is generated from the crystal are these two photons which already carry forth the properties of the mother photon. So then these two daughter photons, as we call them, carry forth the properties of the mother photon. So this is called this pump beam modulation. But having said that, as you know that, the orthogonality is fine at the slit level. But then even there is an issue, because there could be some interaction, which anyways a body is something that we have investigated rather deeply. So I'll come to that. But then having said that, that would be a very small correction as opposed to the conventional method of higher dimension, which is orbital angular momentum, where you actually have an infinite dimensional space and then you truncate it to finite. And so there what you end up is with, these finite dimension, but with a leakage from all the other modes that were there, which you have now managed to block out. So that is how orbital angular momentum works. It starts with infinite dimension, goes to finite. Here we have a bottom-up approach where we go 3, 4, 5. So this is actually much cleaner and in that sense much more orthogonal than the OAM one. But still there will be some correction.
Okay.
Yeah, so I'll come to that anyway. Yeah, thanks for the question. So this, so this was, and so then one of our first experiments in this, we have shown how strongly correlated, spatially correlated, these two photons are. This is the measure of correlation, and so 0.9 is very high. I mean, you never get a 1 in an experiment, and so this led to a series of other work we have done, in which we have shown that not only are these correlated, they are also nearly maximally entangled. And so we now have a system in the lab of 2 photonic qutrits which are nearly maximally entangled. And in this particular work here, this reference 3, we have actually shown, and I think Dipankar Home is also in the audience today. So in collaboration with him, we have shown, this is the theory work, where we have shown how we can actually use statistical correlation measures to come up with measures of entanglement. So we have related statistical correlation measures to actual measures of entanglement like negativity and entanglement of formation. And so one of the problems with higher dimensions is to quantify this entanglement, because what is the right quantifier to use and how do you do it? Avoiding tomography. And so here we have actually shown that, and this is the experiment, this second reference here, which is on the archive, you can see, where we have shown for the first time how we can actually quantify entanglement in higher dimensions using statistical correlation measures, and in fact, a mutually unbiased basis. So instead of doing tomography, the full-blown tomography, by doing, in fact, in this case, measurements in mutually unbiased basis, so which is 2 measurements, and it actually boils down to even 1, which you can see in this paper, we can actually comment on the exact amount of entanglement. And this is very important, because what has happened so far is in higher dimensions, people always talk about bounds on these entanglement measures. So what is the lower bound on EOF? What is the upper bound on something? They don't talk about the actual amount. And so this actual amount you can, of course, calculate by tomography. So you do tomography, then you can derive these things. But if you don't want to do that, because of course we already discussed tomography and its issues for a different discussion 10 minutes back. And so this is a very interesting method, where you can measure statistical correlation measures and then relate them to the actual measures and comment on the actual exact negativity. Yeah, sorry.
Sorry to interrupt, actually.
No problem, but then I don't...
Curiosity. So because you're saying that measure this entanglement of formation, entanglement UAF, etc.
Yeah.
Formal definition of this are they're usually used to quantify entanglement for a mixed state rather than a pure state. Because
it can be for both.
It can be both. It can be both, but
in our case, it is both as well.
Yes, for the mixed state, they require some kind of a purification. Like you have to purify the state up and then do some extremization. It's a little bit complicated. Means I don't know.
Actually, Yorpon, that's an interesting question. So our method, which I couldn't discuss, I mean, cannot discuss this in further detail because of the nature of this talk, but then the method that we have found in which we are relating the statistical correlation measures with these entanglement measures, we actually have these now worked out even for the mixed states actually. So in fact, in this particular reference, you will see some examples of that already discussed. Because also you might realize, although I know you're from a theory background, that you can never have a perfectly pure state in the lab.
Yeah, that's what I was asking. That's the difficulty. It means what is mean
by so that is why that is why it is great that our method does not really necessarily require this particular method of
I see.
So we can actually deal with mixed if we know the type of noise we are dealing with. And so we have done the analysis for different sorts of noise in this paper.
I see.
Have a look. So then, in fact, if we know the type of noise, then we have methods of quantifying the entanglement for such states as well. Yeah. But in our experiment, we have actually managed to create an almost pure state. So experimentalists in the audience will know that we'll never have 100%, but there's always going to be an error bar. And so if we are within that, then we, with a lot of effort, we can actually create an almost pure state.
So that in means the measure for pure state goes to almost like a von Neumann entropy. I mean, the entanglement measuring, like.
Yes. So, and you will be particularly interested in this, right? Because I know that a lot of your work is to do with entanglement entropy. So then in fact, in some, the relation we have found relates negativity and entanglement of formation. But in another work we have done, we have shown how these are related to each other and so on. So that reference is not here. I can send it to you later. So you can see how it varies, how they match perfectly at the maximally entangled, but they're not really equivalent when you go away from the maximally entangled.
I see, because
so the choice, so the choice of entanglement measure actually is important when you are not maximally entangled. And,
yes. And the theory point of view, I know extremely difficult, entanglement of formation. Purification is still
but then that is why this is great, because of course we have been able to relate our Pearson correlation coefficient to EOF as well. So you can have a look at these. Once. But then maybe I move on to the next topic. Okay. And so some of this work is done in collaboration with people abroad and here, but the experiments are all done at RRI, whereas various people have contributed to theoretical developments and discussions. Okay, so now I go on to what Prasanna was talking about in some sense, which is our theory and experiments on quantum superposition principle, Born rule, as well as higher order interference in quantum mechanics. As you can see, interference keeps playing a very important role in many things we do. So now we take you back to the first chapter of quantum mechanics, which is, let's say, the double slit experiment, right? So here we have the quintessential double slits. And the question that I ask you is that if I have one of the slits open, and what am I doing here? I have a source here, I have a detector here. And so what I do is, and this could be a source of anything, right? Electrons, photons, it could be electromagnetic waves, and so on. So I block one of the slits, let's say B, and I open A. And I call the solution to the wave equation, whatever wave equation that may be, let's say Schrodinger equation for argument's sake, is psi A, okay? And then I close A and open B, and I call the solution psi B. The question that I ask is that if I open up both these slits, then what is the solution? Is it psi A plus psi B? And of course, we know that this is what is used in most of our standard literature, actually, this particular thing, because you know that we are plotting mod psi A plus psi B whole square as a function of detector position to get the interference pattern. And so books in quantum mechanics as well as quantum optics are using this as a solution. But of course, if I have asked the question, and of course, for people who already are familiar with this kind of work, you know that the answer is not yes. This is not really the solution. And so then what is happening here? So the previous work on this, for instance, by these authors, so this is from Yabuki's work, is using Feynman's path integral formalism, which of course I'm sure this audience is very well aware of. So if you have a double slit and if you have a source here and a detector here, in this you can see that other than these, paths which cross the slit plane only once, which would be your classically dominant paths, you would also have these sort of paths which cross the slit plane more than once, okay? And so these, as you know, in path integral, all possible paths are allowed, right? Of course, with different weight factors and so on and so forth. So these are the kind of paths which you will not encounter if you block one or the other slit. Only when both are open, these will also come in, and these will contribute to a correction term which will come to an assumption that it is just the sum of what happens when you open one or the other. Okay, and so this was first shown by Yabuki in this particular paper. But then the problem with this paper was that it was of course very nice, but it was a completely theoretical paper by a theorist, and he made assumptions like the slit is of Planck length dimension, and so there were many things in it which made it very, very idealistic in its thing, and also some of the calculations were not quite correct. And so if you want to use this, and for people like us who want to always test things experimentally, that is not going to lead anywhere, because the incomplete calculations and also no experimental parameter came out of that. And so what we went on to do is actually use Feynman's path integral formalism and show how we can come up with a quantity which can be measured in the lab, which will show the presence of this correction term. Okay, and so I'll skip what is path integral for you. But then having said that, if this video is working, then you can see that if you apply it now to the slit problem, and let's say, is this video working?
Yes, the bar is moving.
Bar is moving, but there is no path coming out of it, which is a very interesting situation. So now, of course, people who are sleeping will wake up, hopefully, because the video is not working, right? So then, of course, the idea would be that we would only have, if it was working correctly, you would see paths coming out here which would cross the plane only once, and then you would have paths which would actually go through more than one slit and cross the thing more than once. And so this is what we call in our paper classical versus non-classical. This led to a lot of discussion. We don't mean quantum paths per se. What we mean is these are classically subdominant, and that of course because the dominant paths would be the ones which cross only once. And so then this was supposed to be indicated here, which didn't quite work. But now if you go on to Raphael Sorkin's measure theory approach, and again, this is something I cannot discuss in further detail here, but then I will just go to this picture here, which is clear by itself. So if you have a single slit, then all you can have is, essentially a slit open and you just measure something at the screen. There's nothing very complicated that can happen there. But if you have two slits open, then you can have a probability of both open minus the singles open separately. And in quantum mechanics itself that this is not zero. So this is what is the interference term, right? That the fact that there is actually a finite thing which can result out of subtracting the individual terms from the probability of both, from this both slits open at the same time. So that is what gives you the usual interference, and that is non-zero even in quantum mechanics. So now, according to his theory, if you go to, this is called sum over histories approach to quantum mechanics. So if something is non-zero, you have to check what happens in the order above that. And so now you have to go to the triple slit category. And so if you go to the triple slit, you can construct a similar quantity that is all three open minus the sum of the twos plus the single. So you can see it is plus minus plus. So there is a symmetry in this construction. And so this now, if you expand, if you assume that P ABC, by the way, this is just this term here, is mod psi A plus psi B plus psi C whole square. Okay, and if you go through the algebra, which you can trust is correct, you can basically break it up, as you can see, in twos, right? So essentially, this is the A square, B square, C square, and these are the cross terms, right? And so these are essentially PA, PB, PC. And so if you do some algebra, you will end up with IABC, which essentially is just that, and it will be identically zero. So what is happening here? So what is happening here is that we have made two assumptions. One is that the wave function is the sum of the three individual ones, that is psi A plus psi B plus psi C. And the second, of course, is we have applied Born rule. So now when Raphael first came up with this sum over histories approach, his idea was that, if we did a triple slit experiment, then we would, and if this quantity, which we can measure, of course, in the lab, if it turns out to be non-zero, then it would indicate a violation of Born rule, which of course would indicate something beyond quantum mechanics, right? And so that was the original motivation for this Sorkin parameter. This is called the Sorkin parameter, okay? And of course, I actually, with my collaborators, did the first experiment on this Sorkin parameter, where we actually measured this term and found it to be zero within an error bound. So we bounded this particular term to 10 to the minus 2, okay? And so we can say that we trust Born rule. From our experiment, it is bounded up to 10 to the minus 2. Okay, and after that, series of experiments have happened in which people have tried to measure this Sorkin parameter, and no one so far has measured anything non-zero. Okay, but then comes the catch that in this there is also a second assumption that psi is psi A plus psi B plus psi C. And of course, as we saw in the previous non-working video, as well as of course my descriptions, that this is not going to hold, because it's not just the sum of the three. There will be a contribution, because there is exact equivalence between the path integral. Path integral is a nice approach because it's easy to apply it and do the math, but then there is exact equivalence, as you know, between this and any brute force solution to the Schrodinger equation. So now this will have a correction term when all three are going to be open. Okay, and so this will be because of these paths which will cross the slit plane more than once. And so this particular quantity, the Sorkin parameter, would be non-zero even without violating Born rule. And now this is very important because, of course, all of us have been for the last 10 years trying to, me and an entire community has been trying to measure this and see if they get a non-zero. And then as soon as we would get a non-zero, we would perhaps be excited that there is something beyond quantum. But then before that, you have to hold on and see if the explanation simply lies because of this assumption, because this assumption is also leading to a non-zero. And so, of course, the first thing we did is apply this particular assumption and not apply it, do it properly and see what is the non-zero for my first experiment. Because just imagine you do this experiment and you're very happy with it, and then you come up with a theory where you show that this particular zero that this value that you measured is not quite right. That would be really sad. But thankfully that was not the case, because this non-zeroness coming in from the incorrect application of the superposition principle, or the incomplete application, was of the order of 10 to the minus 5 and so on. So much lower than what we were able to measure. So it was within our error. So what we measured definitely was still 0, and could not have, this was not precise enough to measure that non-zeroness. Okay. And so this particular work here is where we showed for the first time how you can come up with this, how you can use this Sorkin parameter and come up. This is a path integral calculation based paper where we have shown how this Sorkin parameter can be used to measure this non-zeroness which will happen because of the correct application of the superposition principle. Okay, and so this is what the video also had, this sort of paths. Okay, and then we went on to have an analytic form for it and so on, and one of the experiments that happened, we also were doing the experiment, but the one which came 3 days before us on the archive was this from Robert Boyd, which is of course a very well-known group, as you know, in photonics. And so they claimed to measure these exotic loop trajectories of photons in three-slit interference. And what they used is a photonic setup in which this slit, this plane, this material, they coated it with gold. Okay, and so gold actually leads to what is called surface plasmons. And so these surface plasmons led to an enhancement of this effect, of this, these loop trajectory based effects. And that led to a value of the Sorkin parameter, which the normalized version is what we call kappa. And so that kappa was of the order of 10 to the minus 2, and they were able to measure that. However, you have to note that this measured kappa is the value it is because of a material induced phenomena. It is not the simple geometry approach which actually underlies the original motivation for the Sorkin parameter. But having said that, this is what they ended up measuring. And these, even for theorists like Orpon, you can make out that these circles, these are the experimental data. Okay, with their error bar, that's always experiment, right? And this particular line that you see, that is supposed to be their simulation from our theory. Okay, so they are claiming that this experimental data is a good match to what they have simulated from our theory. And of course, even for a theorist, you should be able to see that this is a stretch of imagination to call it a good match, because all you have is experiments at the minima points. There is nothing at the maxima or at the slope. So if you want to match this curve, then you better have points here and here as well. Otherwise, I would, on a bad day, I would match it with a parabola, this particular experimental data. But this is what they claimed is the match between theory and experiment. So our experiment, which was on the archive 3 days later, was actually way better. And so we measured this using the true geometry effect of the Sorkin parameter, where in that analytic paper that we had found that, it is actually scales with wavelength. Okay, so we went really high in wavelength. So we went on an open field and did this experiment using microwaves. And so this is in the centimeter domain. So instead of sticking to the nanometer based photons, we went to the centimeter domain and did an experiment on an open field in a radio astronomy observatory. And this is our kappa as a function of detector position. And again, you can make out the experimental points, and this blue band is the theory. And so of course we have values, both positive, negative, and 0, as you rightly should have to match such a curve. And so this was our experiment in which we did this using microwaves. And also we were able to reduce the effect and increase the effect at will using what are called baffles, which further proved that what we were seeing is indeed this correction term and not some error that we had forgotten to account for, which was the first conjecture. Because when you measure a non-zero for the first time, people always ask you, are you sure this is not a 33rd error that you forgot? And so that wasn't the case. And so this was our experiment on measuring this using microwaves. Okay, and so this was all done in collaboration. And in fact, Anindo is a collaborator here who used to be Orpon's PhD supervisor. So there is a lot of connection here, family connection. So then now we go on to the third one before I go on to ending with the quantum communications bit. So Hong-Ou-Mandel effect. So Hong-Ou-Mandel effect is something I'm sure people like Prasanna would be very, very happy about. You see the pun there. Prasanna will be very happy about it. So this is something which we all learn it in quantum optics. It's supposed to be a quintessential quantum optics phenomena. So it's a ubiquitous effect in quantum optics, and it's used to measure photon purity, photon distinguishability, heralding in optical quantum computing gates, then noon state. There's myriad applications of this Hong-Ou-Mandel effect, which is a very fundamental effect that we all study and some of us also measure. But what we claimed through this work is that the Hong-Ou-Mandel effect need not be a true signature of quantum. And so this is a very interesting thing that we did. And so just a reminder that, this is going to be a beam splitter matrix. And so now if I have this situation, so if I have a photon incident on a beam splitter, a single photon, it will either get reflected or it would get transmitted, right? So these are the possibilities. Now the question you ask in the Hong-Ou-Mandel is that if you have two photons incident on a beam splitter, what happens? And you can find that out by doing your quantum optics algebra, and you will see that these two photons, they will either go, both of them will be transmitted or both of them will be reflected. They won't go 1-1. So they will either both go this way or that way. And that is what leads to the formation of this 2-0-0-2 state, which is this biphoton state, right? So this is what gives rise to the Hong-Ou-Mandel dip, okay? Now, what was prevalent in literature till we came up with our understanding is are claims like this, okay? And so these are claims which are from very important pieces of work. For instance, O's PhD thesis. O is the O of Hong-Ou-Mandel, right? And so then, of course, these are all very famous people in quantum optics, and these are all claims from their work, where they say, for instance, as long as the visibility of the coincidence dip is greater than 50%, no semi-classical field theory can account for the observed interference, or visibility being greater than 50% is clear evidence of non-classical interference. So essentially the claim is, and many other such statements, that if you get a greater than 50% dip in this phenomena, then you are dealing with a quantum phenomena, and then up to 50% is explained through classical electromagnetic theory. Okay, and so this is what was happening. But then we went on to show that that is not quite right. And okay, and I won't go through the math here, but please do have a look at the paper if you're interested. So this is basically the second order correlation function from the semi-classical theory. Now you can see that this correlation depends not only on the time delay tau, which is what it is, right? So at tau equal to 0, you have this dip. But it depends not only on that between the input pulses, but also on the probability distribution of this relative phase. This is very important. So now if you have no control over this phase, the formula predicts a 50% dip, which is what people have been claiming and saying all along, okay? But now if I go on to this probability distribution for the phase, I can see that if I have a uniform randomization over the phase, which is what would happen if you didn't take special care, you will get a visibility of 0.5. But if the phase is chosen from this set 0 pi with equal probability, the visibility is 1. Okay? So essentially, with proper phase control, one can have a Hong-Ou-Mandel-like dip for classical pulses and with a visibility of 100%. And so this is something which hasn't been done experimentally before our attempt. And this is very interesting because it kind of raises questions about the applicability of the Hong-Ou-Mandel in all these applications that we talked about, whether that is foolproof or whether something else needs to be done and so on. And so this is what we went on to show in this paper here. And so we did a completely electrical experiment. So this was not an optical experiment, this was an electrical experiment. And we did that for several reasons, which I won't get into now. But then having said that, here you can see that this is our Hong-Ou-Mandel dip for the 50% case, where we actually don't worry about the phase control. And so this is our approximation of 50. And this is the case where we actually do have precise phase control. And you can see that we have 99.635 plus minus X%, which is actually as close as you can get to 100% dip, okay? And so we also did the photonic Hong-Ou-Mandel, of course, and there we also found 100%, as is obvious. So that you are expecting to find, because this is photons. This is the bunching, that is the usual explanation for the Hong-Ou-Mandel, right? So classical pulses can be used to mimic a 100% Hong-Ou-Mandel dip. So Hong-Ou-Mandel effect thus is not a true signature of the quantum, especially when it is used as a diagnostic for photon sources. So what next? I mean, it's not a doomsday scenario, because if you actually add one more, if you just basically complete the interferometer for the Hong-Ou-Mandel, then you measure what is called the complementarity effect, and that actually will be able to distinguish between classical and quantum. You can't fool the system with complementarity. Okay, and so this is what we went on to show. And here you can see, so this is where you measure the Hong-Ou-Mandel, but if you complete the interferometer, then you can, you have the other beam splitter, then you can actually measure the interference. So what this essentially means is that you have the particle-like behavior from the Hong-Ou-Mandel, and then you complete the interferometer and you also measure the interference pattern. And that is something you can do only with the quantum scenario, where of course it is a true Hong-Ou-Mandel dip. But in the classical case where you have fooled the observer by using classical pulses and phase control, if you complete it and measure interference, you will not be able to measure interference for the situation where you had the Hong-Ou-Mandel. So you can't have both particle and wave exhibited in the same experimental setup in the classical case. So it will not succeed, and that is where it will fail. And so you can use complementarity as a test for the quantum. Okay. And so I'll skip the details here, but then essentially these numbers indicate that that is what we have found. And so the conclusion is that, we have done this experiment. We've shown that, we can actually get 100% Hong-Ou-Mandel visibility with quantum. But then that is not the end of the story. If you do a complementarity experiment, we fail to demonstrate wave-particle duality without changing source setting for the classical, where in quantum we can. So complementarity is a true signature of the quantum. This is just another example of another experiment we have done in which we have dealt with the very fundamentals of quantum physics and quantum optics in this case. Now for the last part of my talk, and here we have Barry as our theory collaborator. For the last part of my talk, I want to go on to something a little more application oriented, which is in fact quantum communication, or in other words, basically quantum key distribution. Because what is quantum in the quantum communication is the key distribution part. And so this we can say is the most quote unquote practical quantum technology. Okay. And why you should worry about it today of all days, you should be worried about it, because one of the most important countries in the world today, we are having the elections, and so there is counting happening as we speak. And so this is where you don't want to go wrong. So if there is something, this is the kind of communication which is of a highest level of strategic nature, right? So the person you vote for, indeed, the vote should go to him or her. Right? And so similarly, there are other such examples of communications where you actually need security also thrown in. Now here I'm talking to you, there is nothing secretive about it. So this is not an example of that. But if I want to buy something with a credit card, or if India wants to tell Russia something in its defense strategy, these are things you don't want neighboring countries to hear. And so here we are doing all this. Currently, this security of communication is being done using classical means of classical cryptography. Okay, so you have the information, it is encrypted in a key, and then the receiver also has the key and is decrypting it. And so this is the general idea of cryptography. But all of this is actually at being risk of being compromised with quantum computers. And so the solution also has to be quantum, and that is where quantum cryptography comes in. So what is wrong with classical cryptography? The idea is that unconditional security is not possible. So here, for instance, the most popular protocol, is the RSA protocol. Okay, and the RSA protocol is based on the mathematical complexity of factoring large numbers. The fact that it is very hard, it's a hard problem to factor large numbers, is what our security is currently hinging on. But here the gentleman Peter Shor comes up with Shor's algorithm, which is an algorithm using quantum gates that can perform factorization in polynomial time. So instead of it being a very hard problem, it becomes a less hard problem. And so once this is going to run on actual quantum computers, then the RSA protocol based security is going to be completely jeopardized. Okay, so the idea is that computational resources grow very fast, and today's hard problem could be solved tomorrow using brute force attack. Okay, and I don't know. Yeah, okay. Yeah. New algorithms can come for classical computers also. Then, of course, there is a realization of quantum computers, which is where the Shor's algorithm will run. My security should be independent of future advancements in computational power, new algorithms, or new technology. That is, it should be future secure. And so this brings forth the need for quantum cryptography, where security is based on laws of nature, or laws of physics, and not on the mathematical complexity of a problem. And so the most important part here is the key distribution, which is the quantum key distribution. So it's a radical new approach to communication and cryptography, which is using quantum mechanics as its source of security. Okay. And so here we have this is something I always like to tell you, that, this Microsoft research, they say that the RSA 2048 challenge problem would take 1 billion years with a classical computer. A quantum computer could do it in 100 seconds. But please take it with a grain of salt, because a quantum computer which will be able to do this using Shor's algorithm, it is estimated that this could be broken on a quantum computer comprising 4,000 qubits and 100 million gates. And we are not there yet. Right? We don't yet have that many qubits and that many gates functioning in the quantum computers that are currently existing in the world. But that doesn't mean that we have reason for complacency, because think about it. So today we don't have it, but the research is progressing at such a super exponential rate that we should be having it in a few years' time. So you don't want to wait for that many years to actually come up with quantum cryptography. So the research on that and the developments on that have to happen now, so that when this actually happens, this is not a problem anymore, because already we would have switched to, let's say, QKD for our security purposes. So you don't want to wait for the computer to be functioning before coming up with a solution, and so that it is not a problem anymore. And so that is why it is very important to do this now. And at our lab in RRI, we're working on several projects on quantum communications. We are working on long distance quantum communications, and in India's first project on satellite-based quantum key distribution, which is quantum experiments using satellite technology. We are working on an integrated photonics-based quantum communication approach, where we are trying to have QKD on a chip. And this is in collaboration with our Italian colleagues under the ITPAR program. We are also working on this DST quantum enabled science and technology program, and a project on quantum teleportation, which is another method of long distance quantum communication. And then we have a project under the Center of Excellence grant that we have from MIT, where we are working on quantum random number generation. Again, a very important tool in making many of this happen, which I won't get into the details of now. So this is our overview on communications. And so in terms of how quantum mechanics protects information, it's essentially the uncertainty principle, no cloning theorem, and quantum entanglement, which are the key ingredients which help in bringing about the security of QKD. Okay, there are different types of approaches to QKD. You can have popular approaches in both prepare and measure based approach and entanglement based approach. And so we have actually dealt with all of them. Why do you need entanglement? Because you can do with the BB84 type, but you need entanglement because you want to go to what is called device independent QKD in future. So at the moment, we are still restricting ourselves to the requirement of the true single photon source, and that is a device. And there are many other devices involved in our prepare and measure based approaches. But if you want to avoid that, you have to go to entanglement based QKD, where it is based on the correlation itself. And so even if the device manufacturer is malicious, you will be okay. And so that is what the world is heading to, which is device independent. So entanglement-based QKD is important for that. So far as our experiments, we have done, of course, different types of protocols. So this is our BB84. More recently, we have done what is called the B92 protocol, which is a modification of the original one proposed in 92. And in fact, these are various pictures of the Alice and Bob setup. I hope some of you get to see it at some point. Now, I'll skip the details, but this is very important. Our key rate is around 50 kilobits per second, and the quantum bit error rate is 4.79. Now, what is quantum bit error rate? Of course, it's obvious that it is the error that is present in this key. And so you want this quantum bit error rate to be below the information theoretic security threshold for any successful protocol demonstration. So there is a lot of information theory based calculation that one needs to do to establish these security thresholds for different protocols, and they're different for different protocols. For the B92, it's 4.8, which means that above 4.8, information theory does not guarantee this security. So because QKD is actually information theoretically secure, so you need to be below this threshold in order to ensure that your key is a good candidate for the ultimate secure key that you need for your strategic communication. And so we have done a lot of work to ensure that our quantum bit error rate is restricted to this information theoretic security bound. And so having said that, to our knowledge till date, the best available setup using this sort of source reported a key rate of around 31.6 kilobits per second and a quantum bit error rate of 10.5%, way above this threshold. And so our numbers are way better in both these, measurable quantities. Entanglement-based QKD also we have done. So this is our entangled photon source schematic, and Alice and Bob setup, again, not going into the details, but then we have an excellent concurrence value for this entangled photon source is 0.995. And this is how you would do it using tomography, by the way. And so this is, to reconstruct the entanglement from tomography. And so our protocol also shows excellent results for key rate and quantum bit error rate. Another development which we have done as a result of these explorations in quantum communications is actually come up with a very interesting simulation toolkit, which gives you a very realistic, what should I say, simulation answer before you do the experiment for the key rate as well as quantum bit error rate before doing the experiment. And so the point is that, QKD is becoming very, very popular, not only from a research perspective, but also from an application perspective. Companies are coming up there, QKD. Globally, it is very practically motivated. So if you want to actually now say, I want to set up a QKD experiment. So you want a simulator or a toolkit which will be able to tell you whether, these components that you're going to set up, what kind of key rate and Q bar is expected from them. But the toolkits which are available in literature, they don't seem to worry about the fact that an experiment is an experiment, which means that each of these components will come with its own errors, as well as the processes have their errors. Detection is never 100%. So what we have done is accounted for all these imperfections and come up with a realistic answer, estimate for these numbers. And also matched it beautifully with our own experimental demonstration, which in fact is India's first free space QKD demonstration, end-to-end demonstration. So before this, there is no published QKD experiment from our country in the free space domain. And so this actually achieves many firsts here. This particular work, if you have a look at it, please do. And so also garnered quite a lot of media attention. This was the IBM blog, where they covered this work and so on. And so this is what I was saying. So there are different toolkits available, but none of them seems to worry about these requirements that we are worried about, which is quick and precise simulation of physical processes considering realistic experimental imperfections, simulation of these processes as they are, source, detection, background noise, generalization and applicability to all existing protocols. So this is what we are working on. And this is important, as I said, because it is becoming commercially viable. So you don't want to set it up and then realize you want to buy more stuff. And that is where this is also going to help you in correct utilization of resources. And we followed what is called the AGIFOL model of software development. Okay, and so these are the comparative results between theory and experiment, and simulation and experiment. And you can see that, the key rates are in the same ballpark. The Q bar, of course, is restricted to 4.8. And so otherwise, if you did not have such a toolkit, you would expect the key rate expectation to be, let's say, 200, whereas what you end up with in the lab is 50. And that is what you don't want. Okay. So the last 3 minutes I want to spend on long distance quantum communications and the need for this. Of course, I hope you understand that quantum key distribution is important. But then, of course, if only me and my neighbor in the lab are communicating, that's not very interesting. This has to be, applicable over a longer distance between the sender and the receiver. So if you want to go to ground-based approaches, then line of sight becomes important. So if you don't see each other beyond a point, even the horizon comes in as a problem. So then it doesn't work. So only a few 100 kilometers you can do with line of sight. You can use optical fibers, but there you have a problem because fibers, there is an attenuation. So every few kilometers, this is the idea, right? It's 0.15 dB per kilometer. So what do? If you want to do some repeater-based thing, then also it won't work because that will violate no cloning theorem. So you have to come up with something unconventional in order to increase the distance in quantum key distribution. There are two viable approaches that are being globally investigated. One of them is the quantum repeater, which is not quite the same as the classical. It actually involves quantum entanglement and its distribution, and using satellite as a trusted node. And we are actually working on both these approaches. This one we are doing under the DST program. And so I'll skip the details of this here, but then the idea is I wanted to go to the satellites one. So this is the idea. So you have a satellite, either it can host the photon source and distribute 2 photons to 2 ground stations, which then through certain mechanisms, these two then get connected, or you can have the sources at the ground stations and one photon goes. So essentially the satellite comes to one of them, exchanges a key, then goes to the other one, exchanges a key, does some XOR type operations, and then these 2 ground stations get connected by a quantum link. And this is the approach that we are following in our lab. And so this sort of gives you an overview of different distances you can reach with repeater and satellite. So the bigger picture is to reach something like this, where you have a satellite, it is just, it is connecting to far placed ground stations, and these ground stations are then connected individually to different, service providers, maybe through fiber networks. So combination of free space and fiber is going to lead to what is called the global quantum communication network, or the quantum internet. And this is what the community is working towards, with different things coming up from different countries, but only one successful so far quantum satellite demonstration from China. And these are the other countries, they have their own programs, just like we have ours, which is the QUEST program. And so this is that. This is the Quantum Experiments with Satellite Technology project that we're working on, which is a collaboration between RRI and the Indian Space Research Organization. So we're already 3 years into the project. And our aim is, in fact, to have information theoretically secure communication over large distances between two ground stations, which are located within India, as well as a ground station in India and a ground station in Canada. So we want to have this long, several thousand kilometer link on one hand, as well as become completely, indigenously, capable with the two ground stations within the country. So that these are the two broad aims of the QUEST project. And so this is my lab actually. And so here, these are the portable ground stations that you see, which are already there. And, so this is our work in progress towards the free space demonstration of QKD across campus. Okay, so I wanted to end with some pictures and some happier times where, this is Jianwei Pan actually, who's heading the Chinese quantum satellite program. And so he was here in January for our last physical conference before all this started, and Arpan recognizes him here on Indo. And so then these are visitors, and I really look forward to having such pictures again from the lab. It's online, can only go that far in communication. So with that, and in fact, I wanted to end with this particular picture. You see this one here with the turban person. This is the Minister of Science and Innovation from Canada. So he came, this day, Arpan, is the same day 4 years ago when the US election results were being declared. And this is just too much of a coincidence not to mention, right? So on that note, I end, I think, perfectly on time, I hope. Yeah.